Hi, I'm Bob Doyle, webcasting from my ITV studio in Cambridge, Massachusetts. I call myself the information philosopher, and I am writing books on information philosophy in a few different areas. One of them is about the work of Albert Einstein. Einstein is basically the source of most of what we know today as quantum physics, although I hope to show that really his contributions were not as appreciated as they should have been at the time of his work, nor are they really that appreciated today. So I want to point out that my blog post today is on the identity, of elementary particles. They are indistinguishable from one another. One electron is exactly like any other electron to a degree that's beyond anything we know in identity. Let me switch to this screen and talk to you about this a little bit more. This is my 10th week of lecturing on YouTube and Facebook and on our local cable channel 8 in Cambridge, Massachusetts at CCTV. I'm very pleased to have been able to do this. I made a few mistakes on the way along, but a lot of it is working now, and I'm very happy lecturing 5 times a week at 3 o'clock in the afternoon for Cambridge and live in case there are people out there who do look into my lectures over YouTube and Facebook while they are happening. Of course, the major use of them will be when we have on-demand use later. I'm just looking here for my lectures, and here they are, and I can bring them up and show you that you can go to my website at informationphilosopher.com, and there you see the website banner in the top, and in the middle of here you'll see there's a lectures link right here. I'm turning it blue and dark blue and white, and there are links to my books, the books in progress. There's a link to my blog, and it's the blog where I tell the story each day of what I'm going to lecture on that day. And today's blog looks like this. But before I get into Einstein, and this is the 10th lecture on Einstein's work, I want to point out that I am trying to complete my book on Einstein's work, which looks like this. And maybe I can put it down on my table here and show you a look of my studio from above. Here I am with my book on Einstein, which is called My God, He Plays Dice. Here you see the control surfaces that I use. This screen on the left has got the blog post, and we'll talk a little bit. I put on the blog an introduction to what I'm going to discuss today about Einstein's work. On the right side, I've got a web page on identity, because that's the key concept that we're going to connect into quantum physics and what turn out to be quantum statistics. So let's just zoom in a little bit closer to see the book itself, and then even tighter, How Einstein Invented Most of Quantum Mechanics. My story is that, or my question I put here on my draft copy, is it possible that the most famous critic of quantum mechanics actually invented most of its fundamentally important concepts? And to me, this is an astonishing thing, and I hope I'm going to be able, with my limited resources and exposure or ways of contacting the world, will be able to tell this story. Because besides quantizing light energy, and indeed its interchangeability with matter, with this famous equation E equals mc squared, and I should say, besides proving that material comes in quanta in the form of electrons, protons, atoms, it was the proof of the existence of atoms that was included in one of Einstein's great papers in the year 1905. So Einstein both quantized atoms, matter, and also light energy today in what we call photons. He was the first scientist to see many of the most fundamental aspects of quantum physics. the physical derivation of the Max Planck's black body radiation law. The idea of non-locality, that there were effects that seemed to be happening over distances that might have implied instantaneous action at a distance, the famous spooky action at a distance. Then the internal structure of atoms in solid state material or crystals and so forth would seem to indicate that material had energy levels with jumps between the levels. That was, of course, what Niels Bohr would bring to us in his 1913 Bohr atom. Then the idea that there's a duality between a wave description and a particle description, and that the wave description seemed to involve a collapse of the wave aspect, which had probabilities that particles could show up in a wide range of places. Then he developed the first understanding of the transition probabilities for atoms to emit radiation or absorb radiation, and that introduced indeterminism into the world whenever matter and radiation interact. He made quantum mechanics a statistical theory in this work, and he always said that it is not a complete theory because it doesn't know everything about each individual particle traveling on some path. And then the work we're going to mention today is the indistinguishability of elementary particles with their strange quantum statistics, which led to the amazing solid state, or what's called the Bose-Einstein condensation of matter into very strange behaving fluid-like things in which many, many particles are all in the same fundamental quantum state. And finally, in 1935, he speculated about what's called entanglement of two identical particles interacting, okay? I say it took the physics community 18 years to accept Einstein's light quantum hypothesis, the photon hypothesis. He saw wave-particle duality 15 years before de Broglie, who introduced a kind of wave thinking about material particles, and Schrödinger, who developed a wave equation, which is the core working equation to solve problems in quantum mechanics, and then Heisenberg and Bohr, who introduced matrix mechanics and so forth. Einstein saw indeterminism a full decade before the Heisenberg uncertainty principle. He saw non-locality as early as 1905, presenting it formally in 1927, but was ignored this whole time. And even his Einstein-Podolsky-Rosen paper, which became to be called entanglement, was something that was considered very confusing and unclear to physicists in that day, even though today we are recognize this entanglement, the spooky action at a distance, which is at the root of what's called quantum computing and quantum encryption and several other things, that it's an enormous development in quantum physics today. Few people remember it was Einstein who first saw that and saw so many other things that now take it for granted in and around the so-called mysteries of quantum physics and puzzling questions about how to interpret quantum mechanics, to which I hope will make a contribution someday. But coming back to today, as I said, it's the 10th week, and I have unfortunately made very little progress in the writing of this book. I have almost half the chapters drafted, and they are online. If you go to informationphilosopher.com/books, you'll find my finished books and this one halfway through. And those of you who are interested, I hope, will turn there and maybe give me some feedback on my early draft chapters. But I've now decided that I'm going to stop lecturing 5 days a week for about the next 10 weeks, because there's an event coming up soon. Let me find this event for us. It is here, and I can dissolve over to that. In April, a filmmaker named Olivier Wright, his name is down here, maybe not so easy to read, will be screening for a university audience, particularly at MIT, but maybe at some other schools like Boston University or Harvard or Tufts, where Dan Dennett is a professor and a major person featured in this film. The film is called PSI, PSI, The Project, and this is a link to the webpage, psi-the-project.com. And besides a feature film in which this young man plays 5 different lives as he toys with the question of whether he's free to be different in the future, depending on what he does in the present. And besides a feature-length film, there will be a series of half-hour lectures by that feature to some degree or other 1 or 2 or 3 of these 9 philosophers that Olivier Wright has chosen to be in his film. One of them is myself, right? Bob Doyle here, Max Tegmark of MIT, famous as the argument, as developing the argument that there are multiple possible universes. He calls the multiverse. Dan Dennett, of course, who's featured here. Michael Gazzaniga, a great neuroscientist. Galen Strawson, the son of Peter Strawson, who's a great impossibilist, arguing against the possibility of moral responsibility. Coricelli here, Giorgio Coricelli, is a psychology and cognitive science specialist. Bob Kane, of course, we've talked about this week. He is the leading libertarian philosopher. Al Mealy and Kane and Dennett are in my book, Free Will. I chose them all as emblematic or representing 3 different positions in the debates about free will. And finally, we've got, hard to read the letters there, I've forgotten Professor Schwartz's first name at the moment, and he is a student or studies the psychology of choice and making choices, because it's called a paradox of choice. He argues that the more choice we have, the more difficult it is to make choices. And we've come in a time in the world when we have so many choices, it's a difficult time. And the more freedom seems to produce, the more concern about being able to make choices. So this web series will be presentable in half-hour lectures, one hopes, at MIT during the day on April 4th coming up. And there may be presentations at other schools around the Boston area. So I guess I could put that in here for just a moment to leave it behind us as we talk about my decision to take some time off from lecturing every day. Now, I have 50 lectures up there, and they cover more or less the entire spectrum of my books. Let me come back to that for just a moment. Scroll up a bit and pull them over to the center of the screen and show you that I have in the left column lectures since November 20th that basically are the material from my book, Great Problems of Philosophy and Physics. That's this one. And then if I go back to my ATEM, you'll see that the second column is 10 lectures on various aspects of free will. And the third column is on different philosophers and scientists, and I feature especially Bob Kane just on Wednesday's lecture this week. The fourth column is metaphysics, and here I've taken various topics and chapters out of this book, and I want to point out that all 3 of these books, come over here for a moment, plus the Einstein book will make my 4th book. That's the last column in these lectures. Click on any of these and it opens up a YouTube and you get to see the 1-hour lecture. But I want to say that I've got to finish the Einstein book, which is this final column, and I've discussed already most of the important contributions I believe few people recognize were initiated by Albert Einstein, and many of them, the credit for the work has been going to other great scientists who made valuable contributions. For example, Werner Heisenberg did his matrix mechanics, and it allowed him to calculate for the first time the energy levels that were hypothesized in the Bohr atom. Erwin Schrödinger came along within a few months and showed another way to solve for these levels that are quantum levels between which there are jumps which either absorb energy as they excite a quantum system, or they emit energy in the form of a photon and so forth. That work by Schrödinger was done in 1926, and that was the wave mechanics. So we have a wave mechanics with Schrödinger, and we have a particle mechanics with Heisenberg. But both of these had been seen almost 20 years earlier in Einstein's 1909 work. My goal then is to try to rehabilitate these findings, rehabilitate Einstein's reputation because of his contributions, which for so many years were just not understood by his colleagues. I mean, we are really dealing with a mind of brilliance, a genius that's on another level from the people who are considered the great founders of quantum mechanics. That's my goal. So I'm planning to take off this time and finish this book by the time we get around to these meetings at MIT in April. And after that, I will return to lecturing 5 days a week. In the meantime, I think my programs may continue to be replayed at least in Cambridge, but there will be no new material added to my online lectures at YouTube and Facebook, if that's where you're looking at them. Okay, with that, we're going to turn to today's, let's see if I have a copy it up here somewhere. Not sure, maybe here. Yeah. This is the copy of my blog post today, and on the subject of the identity of elementary particles. I'll just show you that I basically have two ways of showing this. One is to go here, where I have this marvelous ability to resize the screen that I've developed, and this is called the i5 blog, the Information Philosopher blog, and it's running on this Microsoft Surface. Let me come back to this picture for just a moment and back up just a little bit. See if I can back up to the point where you can see, let's go a little farther back, that on the left-hand screen, I have the ability to size and resize this Surface Pro. It's a wonderful tool. But on the screen in the middle, which you may not be able to see that well, let's just see if I can bring us back to that. On this screen in the middle, it doesn't show up well on the overhead screen, but it basically has an ability that is quite important. And what it does, I will go back to this view, switch to that screen behind me, and this one has the ability to select text and darken it. And I can say, in 1924, Albert Einstein received an amazing, very short paper from India by a physicist named Satyendra Nath Bose. So, working between these screens right now as we go forward, let's tell that story a bit. And let's start right here with the overhead, with the view from this one. I'll bring it full screen. I argue that Einstein must have been really pleased to read the title of this paper, written in English, by the way. It said, Planck's Law and the Hypothesis of Light Quanta. Now, mind you, I'm trying to argue that light quanta had been proposed in 1905, but it's now 19 years later, and very few people are accepting the existence of what just this same year had come to be called photons. It was more attention to Einstein's 1905 work than anyone had paid in nearly 20 years. The paper began by claiming that the phase space, a combination of three-dimensional coordinate space and three-dimensional momentum space, should be divided into small volumes equal in size to the cube of Planck's constant h. Okay? And let's talk about this for just a moment. We're getting into some abstract physics, and it's my hope that I can talk through explanations of what this physics means, so that even just an educated layperson who would like to get to understand what's going on may get there with my help, and I will look for the help from you out there feeding back whether I'm explaining it or not, and you're able to follow this very, very difficult part of physics, and with enormous philosophical implications, as I hope to show also. So what does it mean to have a volume in phase space as opposed to ordinary coordinate space? In coordinate space, we normally think of breaking it up by imagining a coordinate system where we can say this is the start of the system, and as you move to in one direction, let's go this way, you can be 1, 2, 3, 4, 5 of some unit, inches, centimeters, whatever, and we can go in the direction out of the plane here with another dimension, and of course we can have the vertical dimension also, okay? I'm not too good at doing this with my hands. That's the fundamental X, Y, and Z coordinate system we're all familiar with. For example, the streets in Manhattan go north-south streets, east-west, or avenues, I guess, and then east-west streets, and then we have the floors of the different skyscrapers as the third dimension, and we talk about 3 dimensions. Those are in ordinary coordinate space, and the idea of creating such space and such numbers went all the way back to René Descartes, who famously was said to have been lying in a tent in doing some military service, and he noticed a fly on the wall up above him, and he realized that he could tell others where the fly was by counting off towards one direction and then up toward the fly this way, and then go up to get the height of the fly, and that gave him a perception that he could imagine a 3-dimensional space. Now, whether that space is something real in the sense of substantial is a really very deep metaphysical question, which I'm dealing with in my book on metaphysics and future work, in which we may, I think, come to a conclusion that space and time are really abstract, and therefore in the area of, is something that can be described as ideas or information as opposed to anything material. Space and time can be imagined to be empty, and yet we can, even if it's totally empty, imagine laying down a coordinate system to describe where we are in that space. Well, there are a lot of questions come up here. Ernst Mach basically argued against the existence of an absolute space, which is something that Newton had hoped for, that there were absolute points which could be identified, whereas when Einstein worked on his principle of special relativity in 1905, he argued, well, it turns out measurements of this space depend, and they are relative to, the speed with which you are moving. It's possible to kind of interchange time with parts of space so that the space gets to be shorter or longer while the time does the opposite, and so forth. And time then became a 4th dimension in the overall picture of our universe. In any case, this particular phase space adds another 3-dimensional space. And in that space, what we measure is not the distance from, say, some center, but the speed, the velocity, or actually the velocity multiplied by the mass of the particular matter that we're describing in the phase space. This momentum then also can have momentum in 3 dimensions, just like space dimensions. So it can be moving this way, or it can be moving toward you, or it can be moving up, or in general it has these 3 momentum coordinates. So phase space has 3 space coordinates and 3 momentum coordinates, and that's called phase space. Now Planck's constant, h, which you see here, turns out to have the dimensions of momentum times position, or linear coordinate. And so h cubed gives us 3 dimensions, each one of which contains both a momentum and a position dimension. And the fact that space could be considered to be in small volumes of the Planck's constant cubed is an amazing insight into the possibility that somehow space has, and momentum space and position space has a sort of lower limit to what could be considered discrete lumps or sections of space within which strange things happen. And that's what we're going to get to today in quantum statistics, because Einstein is going to discover that there's a small volume and it's impossible to put more than two electrons in one of these h cubed volumes. It seemed very strange. It's an additional kind of insight into the discreteness of the quantum nature of space itself, that there's a limit on the number of particles. You cannot put a third or fourth or a fifth of these electrons into a volume h cubed. And it's different for photons. It turns out there's no limit on the number of photons that you can put into a spatial volume. Now it's space times energy, in this case the photon, but it has momentum, we can describe it that way. No limit on the number of photons we can put in 1 cube of the Planck's constant, but limits on the number of electrons. We'll get to more of that in a minute. What happened was, in this paper that Bose mailed to Einstein, he had counted the number of possible distributions of the light quanta over these cells. And Bose claimed that he could calculate the entropy, which is a very important concept that Einstein had fleshed out in a very important early papers on statistical mechanics in the early 1900s, in the 2 or 3 years before his great papers on relativity and on Brownian motion and on the hypothesis of light quanta. Einstein had worked on statistical mechanics, proved a lot of things having to do with entropy, which Boltzmann also had worked on before him. So there is in the Planck's law, which I describe here in a very simple form, it has a mathematical shape of 1 over the expression here in parentheses of an exponential, where the exponential is raised, the natural number e is raised to the power of minus h nu, which is the energy in a photon. The nu is the frequency of the photon, and the h is the Planck's constant again. And that's an energy, the energy of the photon, divided by Boltzmann's constant times the absolute temperature. Now, there's a lot of interesting physics going on and a lot of important history, because Planck had not only described this action constant, where action is the product of momentum times the space dimension, he also named the k as Boltzmann's constant. Boltzmann himself had used another expression for it, although Boltzmann did use the temperature. And there's this strange -1 added into the parentheses. It turns out Planck had simply guessed at this expression from looking at an earlier approximation to the way in which radiation is distributed over different colors. The radiation law tells how much we have of very high energy radiation, and then down to normal temperatures and very or normal wavelengths like the ones we're familiar with, and then into the red and infrared. So there's a spectrum from blue through yellow, green wavelengths down to red wavelengths. That particular spectrum had been known for many years experimentally. It took Max Planck a few guesses to come up with a mathematical expression that exactly explained this. Before it, a fellow named Willy Wien had an expression, but it was something of the form of a number a, or a constant, divided by this e to the minus h nu, or he called it b nu because he didn't know h yet. Wien called it some a divided by e to the power minus some constant b times nu divided by t. You see he had the basic sense of what was going on, but that -1 was the difference between a perfect reproduction or a prediction of where different colors of light would be in the radiation law and a mistake that went off one end and didn't have the correct values. So Wien had done this in around 1895, and in 1900, Max Planck added that -1 to it. I think I can show that he basically did it by trial and error. It's a rather complicated derivation of the Planck law, and when Planck did it, I think he didn't do any more than come up with what he himself called a lucky guess at putting the right -1 in the denominator and so forth. So this I see, as I try to explain it to you, as a pretty difficult area. It turns out that the Planck law derivation from the time of Planck was done 3 or 4 times by Einstein himself, and Einstein's derivations all were based actually on physical understanding. There was no guessing there. He arrived at the law by developing arguments and putting out an expression and showing that expression explained the Planck law for basic physics reasons as opposed to just guessing. But all of them used classical electromagnetic theory, which really means the Maxwell equations for the electric field and the magnetic field and the two working together that are Maxwell's laws. And when they use Maxwell's laws, you see they were using classical continuous radiation theory. The difference between having something continuous and something discrete is, of course, the essence of getting to have a quantum theory, a theory of quanta, of quantities that are discrete and do things in jumps, as opposed to a theory that does something continuously at all places in space and time, which was the classical theory of electricity and magnetism, very much like the Newtonian gravitational theory, which was a theory that gives values for gravity or the gravitational force in all space and all time. And that allowed us to calculate the motions of particles who had a certain mass being affected by a larger particle like the sun, and explaining the orbits of planets around the sun. The theory of Newton and the theory of Maxwell, the gravitational theory and the electromagnetic theory were both continuum theories. Everything was very continuous. And in order to get the amount of what are called degrees of freedom or modes in the radiation field, which is roughly corresponded to different possible states of that field. Once we get to quantum, it will be really states. They calculated it with this expression, which I won't go into much, except to say that all of a sudden Bose showed he could get this same quantity with a simple statistical mechanical argument, very similar to the one that Maxwell had originally used to derive his distribution of molecular velocities in a gas. This takes us away from Maxwell as a theorist of the electromagnetic field, to a theorist of statistical mechanics. And statistical mechanics, as I mentioned, was formalized initially by Ludwig Boltzmann in terms of developing the expression for the entropy of a mixture of gases, or gas in a box and so forth. But even before that, Maxwell had made a calculation of how many particles were moving very fast, let's say fast ones over here, some who are very slow, and what was the average velocity somewhere in the middle. Maxwell worked that out, and he did it with some what are called functionals, which are just simple observations that the thing that's happening depends on the velocity in the x direction squared multiplied by the y direction and the z direction, the 3 dimensions we just talked about. And the property of depending on squares of these directions led to this sort of an expression that was the total momentum. The total momentum P would be the square, the total momentum squared would be the sum of the squares of the three possible dimensions. So with this in mind, Maxwell had done this. Bose just said, well, Einstein had showed us that the momentum, that a photon has not only energy, but it has momentum. Now, it doesn't have mass. The photon is massless, although it has a mass equivalent in the form of the mc squared, but it doesn't have the mass normally associated with momentum. And Einstein had said, well, maybe the momentum is just take the energy and divide it by the velocity of light. And Bose took this expression from Einstein, and he wrote down, why isn't the sum of the square of the momenta in the x and y and z directions just h squared nu squared over c squared? And this led him to calculate a frequency interval in this phase space. And once again, the phase space is this combination of a coordinate space multiplied by the possible momenta. And he immediately worked out an expression which looks a great deal like, now just hard to see with the way the covers this, but it looks a lot like this degrees of freedom in a continuous radiation field. See that? 8 pi nu squared d nu divided by c cubed. Here we have something similar. It's 4 pi h cubed nu squared divided by c cubed, and then the volume, space volume, this is the momentum volume. He then just divided this by Planck's constant, which knocks out the h cubed, and he multiplied by 2 to account for the fact that radiation has two possible polarizations. Famously with the Polaroid sunglasses, if you take one pair of glasses and put another pair out in front at right angles, no light goes through because there's this concept of light can be polarized, and the resulting vector of Maxwell's description of radiation goes down to having oscillating in only one direction or in oscillating in the other direction. And these two directions are independent. It's something like the two ways in which electrons can spin, which those of you who are interested in that we'll be discussing in a future lecture. In any case, suddenly Bose had a derivation that was purely statistical mechanical. It didn't really make any reference to the classical laws of continuous radiation. It was based only on the number of cells in phase space and the number of ways you could take n photons and distribute them among the possible places in phase space. Well, the story continues with Einstein looking at this paper and realizing there's something very special in it, especially that Bose is claiming to have used Einstein's thinking to get to a fourth derivation of the Planck radiation law. So in a way that Bose later, some of Bose's friends thought was a little rude of Einstein, Einstein translated the paper into German as quickly as he could, sent it off to the Zeitschrift for Physik, the great journal of the day, without even telling Bose. More importantly, Einstein then went on to discuss a new quantum statistics. And it predicted very strange behaviors at very low temperatures for particles whose spin has a unit of 1 unit of angular momentum, which is the Planck constant h divided by 2 pi. In any case, Einstein found that what was in the Bose work had enormous implications for particles with half-integer spin, which is the spin of the electron, and 1 integer spin, which is the photon amount of angular momentum. So particles that have a certain amount of spin, 1 unit, he found has a very different behavior from the particles that have half-integer spin. In fact, he found that you could put an unlimited number of particles with integer spin angular momentum and when you have half-integer spin, you could only fit 2 particles into an h cubed, this basic volume of the Planck quantum of action cubed. Well, already it was hypothesized by Wolfgang Pauli that the electron spin might be a 4th quantum number beyond the standard quantum numbers of angular momentum and energy and so-called magnetic component of the angular momentum. And at this point, Einstein realized that first, the momentum 1 particles, spin 1 particles, because so many could be put together into the same volume, it could be that when temperature got very, very low, these particles could assemble into a condensate, I think he called it a condensation, that could have very strange behaviors because it's a kind of more than cheek by jowl. These particles are all in the same fundamental quantum volume in the universe, and you could put as many in there as you can manage to get there. In order to do that, you have to take a lot of energy away. You have to cool it down to absolute zero. And we had experiments that in that time could get down to a few degrees absolute zero. But today in the 21st century, we can get down to a tiny, tiny fraction of 1 degree within absolute zero, so-called Kelvin scale of temperature. And the most marvelous properties emerge in what today is called a Bose-Einstein condensation. Einstein first saw that the low temperature condensation would be very strange. And we call them today Bose-Einstein statistics. And it turns out that Dirac recognized, I think before Einstein, that the half-integer particles would be doing something different. Today they are called Fermi-Dirac statistics. And partly here is my story. Einstein had done all the things we mentioned at the top of the lecture. Non-locality, quantization of light particles, the calculation or the prediction of transition probabilities, and a number of other things, the photoelectric effect, so-called. And here what he had done was to find there's a totally new behavior that happens when you have identical particles. So if you have 2 particles that both have half-integer spin, you can only put 2 of them, and that became what's called the Pauli exclusion principle. And it turns out that is the building principle in an atom. When you build an atom from hydrogen and double the number of nuclear positive particles, the protons, you get to helium, you can now add 2 electrons, but those electrons have to be opposite spins, and you can't put any more into the first orbit, the first lowest possible orbit in the model called the Bohr atom. In order to add, make a larger atom, lithium is the next one, you have 3 nuclear particles positive, Z equals 3, the atomic number equals 3, and you can put 3 electrons, but you cannot put 1 more into the first orbit. You must put it into the second orbit, called n equals 2. It has an energy related to n equals 2, whereas the first were 1, and so forth. And in that work, Bohr had already explained the entire way the atomic periodic table of elements builds up from adding 1 more nuclear positive particle, 1 more negative electron, and you build up all the periodic table of the elements. Suddenly, Einstein was basically giving you a deeper reason that this buildup had to do with the fact that these are half-integer particles, and there's a new quantum statistics for them because they're identical. And again, I'm just opening up the philosophical, metaphysical aspect of this. The identity we're talking about here is something that's simply not possible in a classical world. We already explored a lot about what it means for 2 similar, apparently identical things to be identical. And I argued that the kind of identity we have between 2 identical things is only the relative identity, that the 2 have the same internal information. But because they are in two different places in the world, they have different external information. This one knows there's another particle next door to it on its left, say, or right, and the other one is the opposite. It is in a different relation to the rest of the world, if there is one, or to the other particle. However, thought of as pieces of matter, if we switch these two and started to count the way that we could distribute them like balls in a box or a set of boxes, which was the traditional way to think about probability, you would assume that having them in this configuration adds 1 unit of possible places, possible distributions, and this adds a second. But with electrons and photons, when you interchange two particles, you do not count them as distinguishable states in quantum physics. So the argument is that particles, elementary particles, have a fundamental indistinguishability that makes them identical to one another in a very different way, physical way, perhaps even metaphysical way, from ordinary balls, the ordinary particles that don't have these quantum statistics. So this is an enormous contribution to understanding of the world. It's a very difficult one to get a handle on. You have to understand probability and statistics and statistical mechanics, and then see that what Einstein did, with a nudge from the mathematician physicist Bose, was to come up with an explanation of how the world works down at the most microscopic level that no one could ever have seen or did see before. So how did Einstein come out of this piece of work? And there, it's the same theme of my book. He rarely gets credit for the other work he's done earlier, and sure enough, in this case, his work became known as Bose-Einstein condensation. And a particle that could exhibit this condensation, which is a particle that has 1 unit of spin as opposed to the half integer units of spin, they are called bosons. Einstein's name has disappeared from the problem and the solution. And today, most people, many physicists, trained physicists, associate this work with Bose because they're called bosons, and Einstein has been demoted from this contribution. And just like the work he did in his transition probabilities predicted the stimulated emission of radiation, it's called, that's the basis for the laser. Light amplification by the stimulated emission of radiation, LASER, the laser, is something that Einstein predicted without ever building one, so he doesn't deserve the engineering credit. But we're talking about a mind, a genius, who is able to see things that no one had seen before him. And today, much of the credit for the things he saw go to other people. For example, Planck, who introduced the H quantum of action, deserves a lot of credit because he was the first to see the need for discreteness in the levels of energy that could be happening in oscillators. But Planck never believed that the energy that's absorbed and emitted between oscillators, or the modern notion of, say, an atom that's interacting with radiation, Einstein was the one who argued that that was discrete. And Planck, for at least a dozen years, never accepted that his work predicted discrete quanta of radiation. He opposed it for the longest time, wanting to hold on to the continuous theory for reasons we've discussed before, primarily because continuous waves interfere with one another in the back of the two-slit experiment and so forth. And Planck could not see how that could be explained. Neither did anyone else for decades. So Einstein's work was sort of in the wilderness all that time, and it today is taught with other people's names. The jumps between the levels that Einstein first saw, the energies themselves, the levels, was 1906, 1907, but it's Bohr who gets credit for claiming there are levels inside the atom. And people teach today that the Bohr atom, when it collapses from a high state to a low state, gives off a photon. Bohr himself fought totally against this, the idea that this was discrete and localized packet of energy, which Einstein had first seen, hypothesized in 1905. And this particular one then, I like to say, and come back to my screen here as we work through that, his work on what led us to lasers, and his work which discovered the Bose-Einstein condensation, either one of these could have made their discoverer a giant at physics. We could imagine another person who did the work on stimulated emission of radiation would be a very famous person, would have their name on that. But Einstein's name doesn't get associated with it because it's been taken in by many other people who developed the standard quantum mechanics and its Copenhagen interpretation. And similarly then, someone could have done the Bose-Einstein work and would be very, very famous, but Einstein's hardly known because anyone who did quantum work before the Copenhagen crew from Niels Bohr, great Niels Bohr, great work really. The point is though that much of what came out of that had already been seen in earlier years. And it's basically forgotten by most historians in today's textbooks, or the work is attributed to others other than Einstein. So this work on quantum statistics that we're talking about today may well have been Einstein's last positive contribution to quantum physics, because some say everything else he did was a negative attempt to discredit quantum mechanics by graphically illustrating quantum phenomena that seemed logically impossible, or at least in violation of his fundamental theories like relativity. Einstein was criticizing quantum mechanics for a lot of very good reasons, but at the same time he was seeing that maybe there's something more fundamental that's wrong in what's going on here. And he came to the belief, or the possible belief toward the end of his life, that the continuum theories of all kinds, gravitation, which he had transformed away from Newton into the general theory of relativity, in which the space itself is experiencing an effect which curves the space in the presence of large masses. So that in a large mass like the sun, the space around it is said to be curved, and things that normally travel in straight lines, like the light from a distant star, when they come to us alongside the star, they get curved, so they appear to come from a different place as they travel. Hard to visualize that. But Einstein's work to question here the continuity aspects, the continuum aspects, the continuous theories of physics, led him to worry about whether there might not be any continuous space and time, that our method of writing down numbers to describe position in space may only be a mathematical tool that we use to go and measure where things, material things, and energy like photons are in the universe in this mathematical formalism that describes the space. But he worried whether there was no such thing as a continuum theory. Towards the end of his life, he began to worry that maybe the universe has nothing but particles in it, and these fields, these forces which we assume curve space in the case of his general relativity, or create quantum events, like the waves in a quantum theory predict where we're going to find particles in the back of the two-slit experiment. Einstein began to think that maybe the waves are nothing but abstract information. That's what I'm going to try to prove, and that maybe the particles of quantum mechanics combine together to create what appear to be continuous fields. When you have gazillions of particles, when you have an enormous number of particles, it starts to look, it smooths out, we average over them, and we describe things with continuous equations. And the Schrödinger equation of quantum mechanics is a continuous and deterministic equation which can be written down mathematically and evolved over time to make predictions of where particles are going to be found. But Einstein is suddenly wondering whether the wave function is just a mathematical tool, which is continuous because math is continuous. And before Einstein, others had concerned themselves with whether or not there are an infinite number of things between points on a line. In other words, an infinite number of points, more than just rational numbers, more than just the irrational numbers. The idea of a dense number of points along a line became a big subject in math. And Einstein was fully aware of the possibility that math is just a tool, an invention of humans, mathematicians, who then, when they turn into physicists, like to believe that all the infinite points have some substance. But of course, Einstein sees they're not substance, they're just information. They're abstract, and the idea that they have values at all points is just because we give them those values, but there is nothing at those points. And if the space itself is changed by the distribution of material objects, maybe then the quantum phenomena down at the microscopic level also may be that, say, in the two-slit experiment, the fact that there are two slits open makes the waves different from the case where we have just one slit open, okay? And that would then suggest that the space is giving us information about where we're going to find particles because of the material around the box, the back screen in the two-slit experiment, the front wall with two slits coming through. When there's two slits, we get one set of waves. When we have only one slit, we get a different one, and it has nothing to do with a particle going through the two slits and somehow doing something that we don't understand. It remains a mystery. But I'm hoping that thinking about Einstein's notion of an objective reality describable by a mathematically continuous wave is not telling us that space itself, whatever that is continuous, but that somehow it's a product of multiple individual discrete objects. And that's where we'll be going in the future. But I think we should stop today and maybe turn on, see if I can get some music to play. I haven't been able to get it to appear lately. No, the answer is it won't play for me. So we'll just talk our way out of this 50th of my lectures on Einstein and going back, metaphysics, problem of free will, and many other great problems in philosophy, and my Wednesday lectures on individual thinkers, which I look forward to doing because I've written up work on over 300 philosophers and scientists, which I hope to share with you in the future. But for now, I'm going to take a few weeks off from doing this, and you'll find my other lectures here at informationphilosopher.com lectures. And this is the work I'm looking forward to in April, where I hope to be able to bring to MIT and maybe Harvard and maybe BU copies of the published edition of My God, He Plays Dice. In the meantime, you can read all of these chapters, the initial chapters. I think I'm up to chapter 16, 17, somewhere in there, on informationphilosopher.com/